Okay, I've had several people asking about logarithms. So I'm going to do a quick, maybe not so quick, spiel on logarithms. Not any section in particular. I'm just going to kind of talk through logarithms and exponents and try to tie the two together and try to make more sense out of it. Um, First of all, let's go back to something squared and let's look at what is a logarithm um, that way, looking at something we know. So let's say we have 5 squared. 5 squared means to take 5 times 5, and we got our answer. But what if I have x squared, and I'm trying to go backwards? Well, we have to have an operation that allows us to undo a square, and that operation is called a square root. And so I go and I take the square root of 25 and I get 5. And in this case, I get 5 or negative 5. So a squared is one operation that says to multiply the base by itself. A square root is another operation that tells me what I had to do to get that squared number. It allows me to go backwards. It asks the question, what number times itself will give me that number? A logarithm is very similar to that. If I have, let's say I have 4 to the 4th power. That means to take 4 times 4 4 times, right? And it ends up being 256. But what if I have 4 raised to some power equals 256? Before the variable was the base, I had x to some power. So the question is what number raised to the 2nd power, and I can undo that by squaring. Well, now the variable is in the exponent. So I know the base, so I know it's going to be 4 times 4 times 4, but I don't know how many times I need to do that to get 256. I could guess and check, but there's got to be a better way, and that's called a logarithm. A logarithm is simply another procedure. It's another operation, just like squared, just like, for that matter, just like addition, subtraction. It's an operation. And the definition of the operation is what exponent, or the answer to a logarithm is answering the question, what exponent would allow me to take 4 to that power and get me 256. The problem is the only base the calculator can work with is base 10 and base e. So I have to have another way of solving when it's not base 10 and not base e, like a lot of things in real life. So that's called the change of base formula. And here's where it comes from. If I take the log of both sides, and when I say the log of both sides, I mean the common log. Common log is when no base is written. It's an implied base 10. So the question I'm asking is 10 to what power equals something. Okay, so I'm taking really log base 10 so I can take it on my calculator. And one of the properties of a logarithm, you got to memorize this one, it's huge. One of the properties of a logarithm says I can take the exponent and move it down in front. So now it becomes x log of 4 equals the log of 256. I'm going to talk and get my calculator going at the same time. Now, when I take the log of 4, that's just a number. That is 10 to what power equals 4. When I take the log of 256, that is 10 to what power is 256. So when I'm solving this problem, remember, this is just some number times x. Well, to get rid of that, go back to basic algebra. I divide by the coefficient. And so I get x equals the log of 256 divided by the log of 4. And I've changed my base to base 10. That is log of 256 base 10. That's a common logarithm. I can evaluate it on the calculator. Okay, so I go to my calculator. I take the log of 256, close your parentheses, divided by the log of 4. Now, think about it. We already did the problem buck before. It should be 4, right? And it is. When you're doing a logarithm, you are simply evaluating the base to what power equals the number you're trying to make it equal. Let's try another one. What is the log base 4 of 39? Think this through. 4 raised to what power is equal to 39? That's the question we're answering or asking. I can throw an x over here. I don't know the answer. So I can rewrite this in exponential form. And I can say 4 raised to what power equals 39. Being able to switch from log form to exponent form is crucial. You got to be able to do that. My base raised to what exponent? This is my base raised to what exponent equals my number 39. Think about it. 4 to the first power is 4. 4 to the second power is 16. 4 to the third power is 64. And so it's somewhere between 2 and 3. But what is it? I don't know. I got to figure out what the value can be. 2 point what? So again, I'm going to take the log of both sides. Bring the x down in front. Divide both sides by the log of 4. Notice your change of base formula. If you have it memorized, great. If not, you can always do this technique I'm doing right here. It's always going to be the log of this number divided by the log of the base. That's the change of base formula. But if you forgot it, just solve it. Take the log of both sides, bring the x in front, divide, and you got it. So we said it's somewhere between 2 and 3, right? Log of 39 divided by the log of 4. And the answer is, just like we said, somewhere between 2 and 3, 2.64. A logarithm is nothing more than solving for an exponent. The answer to a logarithm is an exponent. You are trying to figure out a number raised to what power equals whatever you're trying to find. Okay? The logarithm is a way of undoing an exponential equation. Just like a square root is undoing a square, just like addition is undoing subtraction, just like multiplication is undoing division, and so on. They are inverses of each other. Okay? I think that is about everything on logarithms. Um, I want to do a couple of things tying the log and exponential together. No? Yeah, let's go there. We haven't done that one. Switch to exponential form. Log of x base 4 has to equal 3. Rewrite that in exponent form. My base is 4. The answer to the logarithm is my exponent equals 3. Here's the hard one. Write that in logarithm form. So I know it's going to be the log. My base. What's my base? My base is 3. So my base of my logarithm is 3. The answer to the logarithm is the exponent. So my exponent goes over here. The answer to the logarithm is the exponent. And there's only one other place for the 7 to go. It's got to go there. You got to be able to switch forms from exponent form to logarithm form and from log form back to exponent form. Okay, here's a good example. Why would I need to switch forms? 10 to what power equals 32? How would you solve that? 10 to what power is 32? I don't know. 10 to the first is 10. 10 to the second, oops, not 12. 10 to the second is 100. So it's somewhere between 1 and 2, closer to 1 than it is to 2. So my guess, 1.4. But I don't like guesses. So let's get it exact. What is the x value? What exponent do I need? Well, let's switch forms. The log is base 10. The answer to the logarithm is the exponent. And I'm taking the log of 32. So grab your calculator. Base 10, that is what's on my calculator. So I go log of 32. And it is 1.5. Actually, I was wrong. It's a little bit closer to um, 2 than it is to 1. And again, that's because of exponential growth. It grows faster on the second half than the first half. So it is crucial that we can switch forms from log to exponent and from exponent back to log. Okay, I'm going to build on that one. Let's say I have 17 to the x equals 345. How do I solve that one? Well, now switching forms doesn't really help because it's not base 10, it's base 17. Anytime there's a variable in the exponent, you take the log of both sides. So I'll rewrite this. Push the wrong button somewhere. I'll rewrite this as log of 17 to the x equals log of 345. Bring the exponent down in front, and I'm at the change of base formula. If you have memorized the change of base formula, you do not need to do all this stuff I'm doing. You can just jump right to this last step I'm writing right now. If you know the change of base formula, you can jump right to there. I want to change it from base 17 into base 10. How do you do that? You take the log of this side divided by the log of the base. Base always goes on the bottom. Base on the bottom. Okay. um, hopefully that helps a little bit. Um, we could graph a few. I'm not sure if that is where some of the issues were. Um, I would know your rules. Um, I would know that when you multiply two things together, it's like adding individual logarithms. Okay, you got to know that one. Whoops. When we're dividing two things, it's like subtracting individual logarithms. Okay, you got to know those different things. Um, I think I did one of these earlier. And these are just properties. This isn't definitions of logarithms. This doesn't help you understand a logarithm. But once you understand a logarithm, this will allow you to do some weird things with them. I can write this as the log of 3x to the fourth minus the log of y to the fifth. And then I can write it as the log of 3 plus the log of x to the fourth, just using the two properties we have above. Um, the property we talked about earlier, if there's an exponent, I can bring it out in front. Okay. And again, that doesn't help you understand logarithms. That's just some different ways you can manipulate logarithms if you need to simplify or do some solving or who knows what you need to do with those. Okay. Um, I'm going to stop there. Oh, sorry. One more thing. Just a quick deal. ln means log base e to the fourth. Okay, ln is simply base e. And remember, e is just a number. Okay, and remember where e came from. If you don't remember, pop into my last lecture and it talks about how to get e. It's when you compound something continuously, that's where that comes from. Remember our whole PERT. If something's being compounded continuously, you use PERT. I keep saying I'm done, but I'll go and do another one. Let's say I have 4,000 um, grams of, I don't know, some radioactive substance, and it's decaying at a rate of 4% per day. And it's decaying continuously at a rate of 4% per day. Okay, and so um, my amount that I started with is 4,000. E raised 2. Now, if it's decaying 4% per day, what amount is left? My growth rate, or in this case, my decay rate, is 0.96 because I don't have, let me throw a number in here. I don't have as much left. 100% of what I started with is 1, and so I'm losing 4%, so I have 0.96 of what I had the day before. And let's say how much is in there after 7 days. And we solve. Now, what if I had, and you can just type that in the calculator. I can type in 4,000 E raised to the 0.96. Whoops. Let me do a different E. To the 0.96 times 7. Okay. Sorry, I went the wrong way on that one. I was I was not thinking clearly. If it's decaying at a rate of 4% per day, then it's going to be a negative 0.4. I'm thinking the other formula. Sorry. In the other y equals ab to the x, you would do it that way. In PERT, the interest rate, the E, if it's positive, it's assuming growth. If it's negative, it's assuming decay. And that will come out much better. I don't know what I was thinking on that one. Sorry. Change this to a negative 0.04 times 7. There we go. A little better. So after 7 days, if it decreased 4% a day, you'd now have 3,023 grams left. Okay. Um, one more time. Positive is growth. Negative is decay. For PERT. Okay. For PERT. Positive is growth. Negative is decay. I'm going to do a y equals ab to the x problem. Sorry, our book does a little different. I'm going to use theirs. Let's do this one. Amount equals principal times 1 plus r over n to the nt. That really is y equals ab to the x, but written a little different. Let's say you invest, my smartboard's freaking out for a second. Let's say you invest, come on, $5,000, and we're investing it at 6% interest. Okay, so I have what I started with, my 1, plus I'm investing at 6% interest. But let's compound that monthly. So I'm not going to gain that 6% annual interest every month. I'm only going to gain a twelfth of that every month. But I'm going to compound it each month. So I'm gaining a little bit of interest, and then I'll gain some interest on top of that interest, and so on. So the number of times I compounded is 12. And let's change this up a little bit. The question is now, when will I have $7,500? So now I want to solve. This is one term. So I want to get rid of the 5,000. So I'll divide both sides by 5,000. Grab my calculator. 7,500 divided by 5,000. 1.5. I should have known that. Late night. It's about 7:30. It's been a long day. So I have 1.06 over 12 to the 12t. Now, anytime there's a variable in the exponent, we're going to divide, or we're going to take the log of both sides. So I have the log of 1.5 equals, let's go and get that. Let's get 1 plus 0.06 divided by 12, which is 1.005 to the 12t. Remember, when there's a variable in the exponent, I can drop it down in front. Divide both sides by log of 1.005. My fingers aren't working. Okay, and we get 81.29 equals 12t. Divide by 12. And it's going to take 6.77 years. Okay, I think that's enough. We have some word problems in there and so on. If you're still struggling, shoot me a quick email uh, and try to be a little more specific. Hopefully this will help give you a general outline, and I will do specific problems, even if they are homework problems. So, okay, that's all.